Welcome back to Chem 4300. In this video, we're going to begin Chapter 9 on electrodynamics. Now, in an earlier chapter on electrostatics, we learned how to describe the interaction of an atom or a molecule with a static electric field. In this chapter, we're going to look at the physics and mathematics for describing time-dependent electric and magnetic fields, as well as time-dependent charge and current densities, which may be associated with these atoms and molecules. Now, our primary motivation here is to get a more detailed understanding of the nature of light, which is something you've already learned back in high school physics and chemistry. But ultimately, we want to learn how light interacts with matter. We want to know how to predict the absorption and emission of light by atoms and molecules. And as physical chemists, we want to be able to develop spectroscopy as a tool to learn about the structure and dynamics at the atomic and molecular level. Now, no introductory lecture on electrodynamics can begin without paying homage to James Clerk Maxwell. He started with Faraday's concepts of lines of force in electricity and magnetism, and he worked out the underlying mathematical description that we celebrate today as Maxwell's equations. And through this unified picture, Maxwell discovered that light, for the first time, was an electromagnetic wave. This is something that, 200 years ago, people never understood, but now, with Maxwell, we understand that light is an electromagnetic wave. Now, this was a transformative event in the history of physics. It changed our perception of reality. And as Einstein writes here, since Maxwell's time, physical reality has been thought of as represented by continuous fields and not capable of any mechanical interpretation. So remember, in the last chapter on waves, we learned that all waves, classical waves, were oscillations in some kind of mechanical medium, right? Now we're learning that there doesn't have to be any kind of physical medium that the waves are displacing in. So this is a big change. This change in the conception of reality is the most profound and the most fruitful that physics has experienced since the time of Newton. And Einstein wrote that in 1931 on the 100th anniversary of Maxwell's birth. Now, before we can look at Maxwell's equations, we need to actually take a step back and make sure that we understand how to apply calculus to vector field quantities. So that's what we're going to do first, and then we'll take a look at Maxwell's equations. Now, you're used to pictures like this, which say might be, you might go turn on the news and see a weather map, and you might see a map of some region of the U.S., for example, and you would see like in Michigan, that the temperature is 30 degrees, and in Ohio it might be 50 degrees, and maybe in Florida it might be 80 degrees. And so you can see that at every point on the map there's a different temperature. Temperature is a scalar quantity, and that map of temperatures all across the country at different latitude and longitudes is what we would call a scalar field quantity. So in that case, it's a two-dimensional scalar field quantity. You could also imagine a map like this, where this is a map of the U.S. and parts of Central America, where on this grid of latitude and longitude, at every point on the grid, there's a vector quantity that specifies how strong the wind is blowing and which direction it's blowing. So that's a vector quantity, the strength of the wind, speed, and the direction in which the wind is blowing. So this is an example in contrast to, say, you can imagine a temperature map where it's just a scalar quantity every point on the grid. Here we have a vector quantity on every point of the grid. So this is an example of a two-dimensional vector field quantity. You can also imagine in 3D, so let's say in addition to longitude and latitude, you also had altitude. You can have a three-dimensional wind velocity vector field. This is an example where that vector field would be dramatically changing in different parts of space here. So over here, those vectors would be kind of small in magnitude, perhaps, but over here in the center or middle of this region of space, you would expect very large velocity vectors and moving in very strange patterns compared to over here that would be representative of what a tornado would look like. And so what we'd like to do is to take these kind of vector field quantities and be able to do mathematical operations that will tell us about some of the properties of the vector fields in different regions of space. Obviously here, some major event is taking place, or over here, at least not yet, less of a major event is taking place. So the way we're going to do this is we're going to look at three operators, all based on the gradient operator. The gradient operator is something that we remember from the very first chapter in this class. And we're going to apply this gradient operator to scalar quantities, scalar fields, but also to vector field quantities. So there's a very nice book here I used when I was about your age called Div Grad Curl, which I think is in a much later edition than now. But there's a lot of books out there that can help you understand more about these kind of vector calculus operations. We're just going to review some of the basics here. So this gradient operator is something you remember from the first chapter, as I said, and this was something that we applied to the scalar potential, which was the potential energy function, right? So we know that at all points in space, there was some scalar quantity, the potential energy, and from that quantity, we could derive the force at that point in space that would be acting on a particle in that potential energy scalar field, right? So this was the equation that we had. We just applied this gradient operator onto that scalar field, and we got a vector field, which is the force vector at every point in space. But we can also imagine if we were applying this to not just a scalar field, but let's say we were applying it to a vector field, how would we do that operation? Well, when we're talking about vectors, we know that when we're doing these kind of operations, there's two ways we can do it. We can do it as a dot product, and this is called the divergence of the vector field. So if you apply the gradient operator to a vector field as a dot product, you get a quantity which is called the divergence, which we'll learn is a scalar field quantity as the result. And you can also do a cross product. So when you do the cross product of the gradient operator with a vector field, you get another vector field back, which is a vector field that represents what we call the curl of this vector field. All right. Don't worry, we're going to give some more pictures here where you can understand better what these operations are telling us. So let's start with the divergence. This is going to tell us about how the velocity vectors, something about how the velocity vectors appear in space in terms of whether there's a source or a sink of this type of vectors, quantities. So the divergence, which is this dot product, if you apply it to your vector field quantity, like I did here, then you're essentially at every point in space just taking the derivative, partial derivative with respect to x, y, and z, and when you're done, you're just going to get a single number defined at every point in space. And what that number does is it tells you whether certain regions of space are regions of what we call positive divergence, or negative divergence, or convergence, or a region where there's no divergence at all. So you might think, for example, of say a velocity vector field for water as it's going down a drain. So if you think about the water velocity vectors as it's going down a drain, then you can see that you have a region of what we call convergence or region of divergence. Or if you think about water that's bubbling up out of a fountain, you might have a region of positive divergence for the velocity vector fields. Or if you're just looking at water just flowing down in a stream, there's no source, there's no sink, then you have a region of zero divergence. So by applying the divergence operator, we can learn something about what's happening in a vector field in a particular region. All right. Now, the curl of a field also gives you a vector field back, and of course the curl is a cross product, and cross products we do with these expanding out this determinant here, and we're going to do it this way, where we have the unit vectors up here, we now have the partial derivatives here, and then we have the components of our vector field for some point in space there, and we apply them, and we get this quantity out here. And what this operation does is it gives you back a vector quantity at each point in space, but the size of that vector quantity tells you about how the vector field is circulating about that point in space. It gives you the circulation per unit area. And you can use something called the right-hand rule with this, where if you curl your fingers along the direction of the circulation, then your thumb will point in the direction of the curl. And the more it's circulating, think about that tornado, for example, the more it's circulating, the longer that vector is. All right? And so this is another operation that tells us something about what the vector field quantity, which used with the divergence, helps us understand, if we could look at our weather maps, helps us understand what's going on in that particular region of space. So as another example, here is a wind velocity vector field. It's a 2D field for the summer of 26, around the Caribbean Ocean and the Atlantic Ocean. And during that summer, there were a number of hurricanes. And you can see what the wind velocity vector plot looks like. It's kind of small to see the vectors here, but if you look carefully, you can see their vector quantities. And you can see that there are regions of very strong curl here, here, and here. And there are regions here where the curl is not so high, right? So these are the regions of strong curl. Now, in this case here, you can also predict which direction the curl is pointing. So if I went over here and I curled my fingers in the direction of the wind velocity vectors, which are curling around, then my thumb would be pointing out of the board. So in this case, these are all curling in a counterclockwise manner. And so the curl vector is pointing out towards, from out away from the surface here. Interesting point, if you were looking at hurricanes in the southern hemisphere, they would be swirling around with a curl that points towards the surface. In other words, they swirl around in a clockwise fashion. And that's, as we've learned earlier in the class, that there's Coriolis forces due to the Earth spinning, which is responsible for these differences between the northern and southern hemisphere curls of the wind velocity vectors associated with hurricanes. Okay. Here's another example here where you might have a bathtub drain, where when you pull the plug and you watch the water go down, you know that you have a region where the divergence is negative, so you have a sink, it's going down, and you also have a region where you have a curl that's pointing, in this case, it's moving clockwise, counterclockwise, sorry, in this picture, and so we have a curl that's pointing up above at the drain where it's swirling around. All right. Okay, so I hope that gives you a good picture of these two operations, the divergence and the curl, and they're not so scary after all. You just take your vector field and you apply the divergence and you learn about sources and sinks, and you apply the curl and you learn about circulation in different regions. Now, what we're going to do is we're going to take those mathematical operations and we're going to apply them to electric fields and magnetic fields. And that's what you need to understand what Maxwell's equations are going to be telling us. So now, let's look at Maxwell's equations. So these are around the 1860s that Maxwell unified the field, which are now summarized in these equations here. And let's get familiar with the symbols here. So this is going to be the electric field, the electric vector field. B will be the magnetic vector field. Rho will be the charge density, scalar field quantity. And J will be the current density, vector field quantity. So J tells you the current that's flowing and the direction, whereas Rho just tells you the charge that's present and which is varying in space. And so now we have the electric and magnetic field, and the relationship among these scalar and vector field quantities are given by Maxwell's equations. These are the constraints that for these fields to coexist with each other, they have to satisfy these equations. And the only thing left here that I haven't mentioned is mu, which is the magnetic constant, just something you can look up. It's a permeability of free space. And epsilon, which is the electric constant, which is the permittivity of free space. These are just constants that you can look up. And these are the constraints that have to always be satisfied for these fields. And you can see they involve divergence and curl. So what we're going to do is we're going to look at each one of these terms, A, B, C, and D, and see how they physically make sense and what they physically represent. So we're going to have a tour of Maxwell's equation with your understanding of grad, div, and curl, right? So let's start with Gauss's law. It tells us that the divergence of the electric field is equal to the charge density divided by this constant, the electric constant. You can actually derive this from Coulomb's law, and this is something you might remember from the first chapter where we talked about Coulomb's law, is that if you have a positive charge, that the electric field lines emanate out from that. So that's a region of positive divergence. If you have a negative charge, then the electric field lines converge into that. That's a region of negative divergence. Obviously, here we have a dipole, so we have a positive and negative divergence together. And here we have two positive charges, and so we have two positive divergences next to each other. So that's all that the first term is telling you. It's telling you that if you have some charge present, then you're going to have some kind of divergence, either positive or negative, around that region. And if this was equal to 0, then the divergence would be equal to 0, and there'd be no sinks or sources. That's all we get from Gauss's law there. Now, Faraday's law of induction tells us that the curl of the electric field is related to the rate of change of the magnetic field vector magnetic field vector quantity. So this is something that you may learn about in your physics class. You know that if you take, for example, a loop of wire and you had a bar magnet and you plunge that bar magnet through the loop of wire, that will induce a current in this wire, and you can measure that in this circuit here. And what's happening is that, of course, as you plunge this magnetic bar through this wire, what you're doing is you're creating a swirl of electric field around that change in the magnetic field direction. So remember that this curl here represents a circulation of electric field, and that's going to be generated by a changing magnetic field. And so this change in magnetic field creates a swirl of electric field, which then induces the current to flow, and that's what we detect here. So that's Faraday's law of induction. That's the second one here, and it's just telling you that a changing magnetic field will induce a current, induce electric field swirling around it, which, if you have a conducting wire, then the current will flow in that wire due to that electric field swirling around. Okay. Next, we move on to Gauss's law for magnetism, which tells us that the divergence of the magnetic field is 0. And that makes perfect sense because we all know that there are no magnetic monopoles. There's no magnetic charge. Magnetism, as we learn, always comes as dipoles. We can have a north pole and a south pole, but you can never have an isolated north pole and an isolated south pole. So there is no magnetic charge, so there can never be a source, there can never be a sink. And so this is true. This relationship here will always be true for magnetic fields. All right. So that's straightforward. And finally, we come to what's called the Ampere-Maxwell law, because it has two parts. It's telling us that the curl of the magnetic field will be curling around, in the sense, these possible sources. So one is a current flowing in a wire, or some kind of current velocity vector. And the other one is something called the displacement current. We'll come back to that in a second here. Let's talk about this first one here, the Ampere's law. This tells us that the magnetic fields will curl around a flowing charge. So if this was a wire and we curl our fingers, or we put our thumb along the direction of the current, then our fingers will curl around the direction of the magnetic field that the magnetic field is doing. So this part right here is just telling us that what you know is that as you have current flowing down a wire, there will be a magnetic field that's curling around the direction of the current flow. That's what's called Ampere's law. And this one here is sort of, Maxwell proposed this one, and this was proposed by Maxwell. It wasn't known at the time, but he put it there to kind of make all the equations consistent. He needed something that was analogous to Faraday's law, where the changing magnetic field caused a curl of the E field. He needed to put this term in here, which was a changing electric field caused a curl of the magnetic field. And so this is what's called the displacement current, and that makes all of his equations consistent. And it was the discovery of this term right here which was essential for him to come up with the discovery of light waves. Okay, so that is our tour of Maxwell's equations. And you can see now that they may look scary, but now you understand the concept of divergence and curl, that they are actually very, very sensible here, that the divergence of an electric field is going to be related to whether there's a source or a sink, so you have to have some charges around. If there are no charges around, there's no divergence. Likewise, there's no magnetic charges, so the magnetic field can never have a source or a sink, and we always have the divergence of B being 0. We saw here that Faraday's law told us that a changing magnetic field will cause a swirl of electric field around it, and a changing electric field will cause a swirl of magnetic field around it, and it will also be generated by a current that's flowing along a direction will cause a swirl of magnetic field around it. Now, if we had magnetic monopoles, then we would have analogous terms. We would have a magnetic charge density here, and we would have also up here, we would have a magnetic charge current that would be in this term to make everything symmetric, but there are no magnetic monopoles, so that's always equal to 0, and we have no magnetic current. That part's not showing up here, but all of this is very straightforward to understand once you understand what divergence and curl are telling you about the vector field quantity.